like I have actually under this shirt, I'm wearing a shirt that's for a pizza place in Kentucky. So not related to the moon at all. So welcome everybody. I believe we are up on YouTube now, which means I can say hi to everyone. We are going to be talking about lunar geology today. For those of you who are joining on Zoom, please do let us know. Actually, for those of you who are joining us anywhere, please let us know where you're joining from. It's our little tradition here to share where you're from, and sometimes the weather there as well, which I don't know about you all, but here it is very depressing. It's just pure cloud here. What about you, Chris? I assume you're all cloud too, right?
Yes. Well, we had a little bit of a good run there a few nights. So I didn't get out myself because I was prepping for things like this, but.
And now is a good time to thank Chris Vaughn more publicly for all of the things he does at Rask.
I sacrificed the clear nights to be slaving at the computer for prepping Insider's Guide. Yeah.
Which are very appreciated.
I'm here all week. Tip your waiter.
I have only been able to get astronomy done in the morning these days, it seems. And by get astronomy done, I mean look at my window and go, oh, isn't that nice? So it's been quiet here too. Thanks everyone for letting us know where you're joining from. All over the place this time. Great to see you all. Today, because we have some exciting stuff coming up in the sky in the next 2 weeks, we're going to be specifically to do with the moon. We're going to be talking about lunar geology today. Chris, are you going to save those two events for big reveals in the talk?
Save it. No, I think we'll dive right in, I think.
Perfect. Okay.
Yeah.
Those two events, in case you're curious, are November 11th at 6 p.m. Eastern time.
Well, it has error bars on it, so I'll get into that. But yeah, okay. Thursday night,
we have the Lunar X happening, which is everyone's favorite lunar observing thing. It's when you see a little tiny X along the terminator. Chris will go into more detail. Sorry, spoilies. Don't mean to spoil the fun. And we have another event coming up on Friday, November 19th as well, which now I'm afraid to spoil.
That's okay. We'll be there in a moment. All right. I just want to open up this picture too. Good. Yeah. So what I thought we would do is we would cover off the preview of the two celestial events, the two moon-related events, and then we'll dive into some aspects of the moon's geology, and things things to help you appreciate the moon a little bit more when you're looking at it. And then we'll at the end I've set aside time for some guided tours of a couple of spots on the moon. And I when I sent my notes to Jen, I said this is part one of. Because I think that from time to time we could return to the moon and focus on a particular area and highlight some aspects of the moon that when you're just looking at it and getting impressed by how pretty it is, you may not appreciate the science that you're seeing when you're seeing the moon. So we'll get into that as well. All right, so what I'm going to do is I'm going to share my screen and dive in. Here we go. First thing I'm going to do is I'm going to show everybody this picture. So you've all heard, and by now all of you have heard of the Lunar X because we just mentioned it. But at the same time, when the Lunar X is occurring, there's also another feature called the Lunar V that occurs. But wait, there's more. So we'll get into that here. Let me just get my notes in line here. So a few times a year around the first quarter moon, the position of the terminator lands just right, that it sweeps across a set of craters named Purbach, Lacaille, and Blanchinus. And the adjoining rims of those craters are high enough elevation-wise to be illuminated first and the surroundings dark to produce an X shape that's visible on the moon. You can see it with binoculars if you've got them on a tripod. I find if they're shaking, it's a little bit difficult, but it's visible. And then due north of that, north of the moon's equator, there's a V-shaped This is up near the crater Eucurt, I think it's called. And then in this picture, you can see down here near the southern pole of the moon, there's an L shape. And what I use to find this pattern is I look at this little, let me just zoom in here, make this a little bit bigger. I look for this very distinctive trio of craters that look like Mickey Mouse's face with the ears, which is quite obvious in binoculars and telescope. And you could potentially look for the L. And I'm even seeing maybe a backwards E here. So that's why I've got pick any crater and you've got LOVE on the moon. All right. So let me just show you the circumstances of that. I'll bring it up here.
For those of you who are new or simply don't know because we haven't used the software in a while, I believe Chris is using Starry Nights, which is different from Stellarium, a little bit more powerful.
Yeah, so what the Starry Night lets me do is actually travel from place to place and do a little bit more magic than I can normally do just with Stellarium. So this is the circumstance for the Toronto area. So what happens is that as the terminator sweeps across the moon, the X gradually appears, peaks in intensity, and then starts to fade out. And you've got 3 to 4 hours time window in which to do that. I'll bring up you can put the link in the chat of the lunar visualization tool, but I'm just going to open it up here and show everybody. So I really like using this tool put out by NASA. And what it does is it shows you how the moon will look at every hour of the year for 2021. And so what you can do is you can dial in November 11th at say 2300 UT. So this works in universal time. And there you can see the little X is starting to form in the bottom of the moon. If you go ahead an hour, so you need to go the next day at 0 UT, and you'll see it stronger. And that this would correspond to 7 p.m. Eastern time. What's that? 6 p.m. Central, 5 p.m. Mountain, 4 p.m. Pacific. So the folks on the West Coast will have this happening while the moon is in a bright daylight sky. And you can still look at it with your telescope as long as you're careful to avoid the sun, of course, because the sun might still be up in your time zone. But the trick there is if you've got some polarized glass, either say 3D glasses from the movies, and you rotate those over your eyepiece or just tilt your head, you can make the sky around the moon darken and the contrast on the moon brighten. So you can actually enhance the appearance of the moon by using the polarized light to diminish the sunlight around the moon. So there's November 12th at 1 UT, which is 8 p.m. On Thursday night, and so on and so on. So I'll just show you so this phenomenon, and here's the simulated view of that in Starry Night. So the phenomenon is called Pareidolia, which is the phenomenon where humans make patterns. The human brain makes patterns or recognizable shapes out of things that they see. So I think that's about all I was going to say about that. The other thing is that the next one, so that NASA website has not yet posted the 2022 model for the year. So we can't go ahead and use that to look ahead. I did notice that reports that there's a Lunar X happening on the January 9th. So let's see if I can do January 9th here. I'll just make sure the moon is centered on the view here. Center this up. Go ahead.
As you're moving ahead, I will also mention that the Lunar X happens every cycle for the moon. It's just that sometimes it happens when we here in Canada can't see it. That's
right. Yeah, the Terminator always sweeps past those craters, but much of the time it hasn't risen or it's already set for us. Yeah, so there's January 9th. So on that date, the moon will be, for Toronto at least, well up in the western sky. And so it should be visible for folks on the East Coast and through much of Canada as well. So all the way across the country. So if you miss,
go ahead.
Yeah, no, it's all right.
There's a question in the chat from Warren, and I'm not sure which angle they're talking about. What is the sun angle approximately? I don't know if that means the angle of the sun on the Lunar X or in the sky? Do you know?
Well, when the moon is at first quarter, the moon is approximately 90 degrees, 90 angular degrees away from the sun. So it only occurs, this particular shape only occurs at first quarter when that 90-degree angle.
From Earth. So if I'm Earth and you're the sun, the moon's directly 90 degrees to one side.
Off to the side, yeah. Yeah.
Thank you.
If you look at the Observer's Handbook, the monthly pages, there's a number in there called the Co-Longitude. And that Co-Longitude is actually the coordinate on the moon where the terminator is. And some of our friends have created spreadsheets that will enable them to predict the Lunar X occurrences by typing in the monthly co-longitudes and interpolating between the dates given. So stay tuned. If you follow my skylights, or and as we go into next year, we'll be mentioning it when they come up again. So we will make sure nobody misses them.
I'll link your
one other thing one other thing that I did here is I said, what would the Lunar X look like from the moon? Lunar X from on the moon. So I'm not sure what I did. Oh, I think I did. The point I was making here is that those three craters that are forming the X are doing that because the sun is just rising on the moon at that point. And so if I advance a couple of hours in here, you'll see the sun rises over the horizon. So that's the terminator sweeping over that part of the moon because the sun is rising at that point. So yeah.
There's a quick clarification from Warren in the Q&A, which was the sun angle on the moon, which would not be quite zero. So it'd be like right between just above the horizon and maybe like 2 or 3 or maybe 4 degrees. I guess we could do the math, but essentially it's just around sunrise. So the sun would only be a couple degrees above the horizon. Sunrise
the phenomenon runs for 2 or 3 or 4 hours. So there's actually a range of sun heights that will work. It's not a blink and you'll miss it event.
Cool.
Yeah. All right. So that's the Lunar X event. And then next week, we have a partial lunar eclipse that is almost a full eclipse. So this is the second eclipse of 2021. It's going to happen a day before apogee. So that'll mean the moon is a bit smaller. And all of the moon is going to enter the Earth's umbra except a small sliver. So let me just bring up the circumstances here. So this is now a view in the sky from Toronto. Now, the sad aspect of this is that it's early in the morning, so between 1 a.m. and about 5 a.m. in the morning on the 19th of November. So don't wait for November evening, right? Set the alarm on the 18th to get up early on the 19th or stay up late. But it'll be nice and high in the sky. It'll be near the Pleiades. So there's the Pleiades star cluster. And the moon is moving this way through the Earth's umbra and penumbra. So the umbra is the zone in which none of the sun is visible for an object inside the circle. And the penumbra is the zone in which at least a bit of the sun is still visible when you're passing through the penumbra section. And as we journey through the time here, I'll just advance through here. You'll see the moon's eastward orbital motion carries it into the umbra. So first it enters the penumbra around a little after 1 a.m., so about 1:02 a.m. And then you may see the moon slightly darken at that point, but there's still going to be sunlight hitting all of the moon at that point, some sunlight, so it won't be darkening all that much. The time when you'll begin to see the bite out of the moon will start around here at about 2:18 a.m. Eastern time or 7:18 universal time. And that's the point at which the limb of the moon, let me just get this a little bigger, makes contact with the umbra of the Earth. And so from this point on, you'll start to see the bite out of the moon come in. Now, at maximum eclipse, the moon is not quite close enough to the ecliptic. See how the moon is missing the ecliptic. So the moon's orbit, I'll just draw the moon's orbit on here for you. So there's the moon's orbit. You can see it's south of the ecliptic, But you can see these lines are converging. So we're not quite there where they'd cross over and be totally inside it, but there's just a little bit that escapes the umbra. So let me just carry on. So greatest eclipse is about 4:02 a.m. So that's around here. Now the software isn't actually doing a great job of conveying this, but what you'll see is that the 97% of the moon will be the darkened reddish coloration, but you'll have a very bright white strip of the edge of the moon just sticking out past the edge of the shadow. So it won't be a so-called blood moon or dark red moon. The other day I did a tweet about the moon, and I used the tomato emoji instead of a red moon. And I thought, yeah, let's get the media to use a tomato moon instead of a blood moon. I think it's a little less violent. So yeah, red tomato. So yeah, so that'll be about 4:02, and then if we keep going, then the moon will start departing the umbra, and by about 5:47 a.m. So as this edge of this umbra is the transition between a dark moon and a lit moon. It's not being shown very well in this simulation, but the fact that people could see the curved shape of that shadow on the moon even long ago in ancient times was evidence that the Earth was a sphere and producing a round shadow onto the moon. Whether or not they knew the moon was a sphere, any extended object with a curved shadow on it must be caused by a round object blocking the sun. So around 5:47 a.m. is when the moon will last touch the umbra. So there'll be no more bites out of the moon at that point. And then you've got that slightly darkened moon until about 7 a.m. Toronto time. So by the time we get to the later stages of the eclipse, even folks in the west coast of Canada will see the darkened portion of it. So I thought I would show you what the eclipse would look like from the moon. So that's what I can do in Starry Night that I can't do as well in Stellarium. So what I did is I parked us on the moon near the south pole of the moon. And remember that southern part of the moon is failed to enter the shadow. So it should still see some sunlight. So what I have is the beginning of the partial phase here. And as I advance time, you'll see the moon. I've sped it up. You'll see the moon come across. And then boom, greatest eclipse, still a little bit of sun peeking over around the Earth, illuminating this section of the moon where we're parked on. And then so at the point where these two circles depart one another is the end of the umbral phase of the eclipse. So there you go.
That's the end of the penumbral phase of the eclipse, right? Because the penumbral phase is only when the sun is somewhat covered.
Yeah.
Yeah.
All right. So that's the eclipse. Maybe you put the eclipse-wise links in the chat. Those are Fred Espinac does a detailed breakdown of every lunar and solar eclipse on his website, Eclipse-wise, and those are great resources. And his information is also incorporated into the annual Observer's Handbook, our Observer's Handbook.
I'll also mention that Linda was in the chat. Linda is a volunteer from Sudbury Center, and Sudbury Center is streaming the eclipse with timeanddate.com. So that link is also in the chat in case anyone wants to watch the live stream.
Fantastic.
That's going to be 2 a.m. to 6 a.m. in Eastern time. So kudos to all of our volunteers who choose to stay up that late.
Yeah. Well, I was telling Blake, our friend Blake Nancaro the other day, that I have 6 of the double stars in the program left to get, and they're all winter doubles. Things like near Lepus and Orion and things like that. And so it might be enough of a good excuse to set the alarm to do the lunar eclipse.
If the weather is good, then you could get those last couple double stars.
Yeah. Because I mean, me personally, lunar eclipses are cool. To me, they're evening cool. I don't know that they're pre-dawn cool, just personally.
And I'll also note, I was looking through the Observer's Handbook for 2022 earlier today, and from what it says, I haven't double checked, I'm sure it's accurate. There are two total lunar eclipses next year that will be visible from North America. So there are more options in the future if you're not willing to stay up until 3 a.m.
Yeah. Yeah. And weather this time of year is a little dicey too. So let's cross our fingers. All right. So I thought what I'd do now is give you a rundown on the moon's geology, and as I said, some things that you can be mindful of when you're checking out the moon, and some interesting aspects that I think you'll be fascinated by. So let's first talk about the way things are named on. So the terms Maria for the dark areas and Terra, which we don't often hear these days, but in older times, the bright parts of the moon used to be called the Terrae, 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 Latin words. Those were actually coined by Galileo when he pointed his small telescope at the moon and began to understand what kind of a world it was. He actually coined those expressions of mare, which is seas, oceans, for the dark areas, and terrae, which is land, for the bright areas. But the person that we kind of attribute the modern naming of the features of the moon that we have today is a Jesuit priest. So he's a religious priest named Giovanni Ricciolini. And in 1651, he produced a map of the moon. And what he did is he assigned names to all the different mare regions and major craters on the moon. And he did something interesting, a couple of interesting points about that. So he decided that he would use living and dead scientists for the moon, and philosophers, because in those days, philosophy was kind of mixed in with science. And he put the more ancient science and philosophers in the northern hemisphere of the moon, and he put the more modern ones in the southern part of the moon. And he also placed teachers and their students together. Let me just see if I've got this. This is the view with the craters named. Yeah. So here you can see an example where we've got Plato, Copernicus, Tycho, people like that. Now, the section of the moon on the left-hand side here, which is the moon's west, is called the Oceanus Procellarum, or the Ocean of Storms. And fittingly, Ricciolini decided to put the scientists that were promoting the heliocentric model of the solar system in the Ocean of Storms. So he put Copernicus, Aristarchus, and Kepler in the Sea of Storms, because as a Jesuit priest, he was teaching the geocentric model of the solar system. So these were kind of troublemakers in a way. So he put them in the Ocean of Storms. Let's see. And he also had some fellow Jesuits that he honored. So he put Grimaldi. So Grimaldi is this crater here, this dark one near the rim. He was a Jesuit, as well as Clavius. And Clavius is the giant crater below Tycho. And he was also a Jesuit. So he got nice, very easily spotted, prominent features. So that's kind of neat. So I hadn't known that about the Oceanus Procellarum, and also the logic behind his naming. Mm-hmm. Let me just go back to the centered moon here again. Here we go. So the mare are all named after states of mind and feelings and things like that, or weather. So we have Mare Imbrium, the ocean of clouds, Mare Serenitatis for serenity, Tranquillitatis for tranquility, Vaporum for vapors, Mare Cognitum for, thoughtfulness. Nubium would be darkness or cloud, darkness. Humorum for humor. Fecunditatis for fertility, and things like that. Some of the more modern names, though, broke the mold when we discovered a few new things. So a few of the features that are around the edge of the moon were not really known to him at that time, but we now know of them. So there's a Mare Orientale around the western limb of the moon. That's now, ironically, Orientale means the eastern sea, even though it's in the western side of the moon. And that's a confusion between east on the Earth and east on the moon, which we can come back to in a bit. And as well, we have two of the big mare that are named after human explorers. One is Humboldtianum, which is over here on the, I think it's on the, here it is, in the northeastern corner. And we have Smithii, which is around the corner of the eastern horizon of the moon. So those were explorers. There's also a Mare Moscoviensis on the far side of the moon, which wasn't discovered until later. All right. So now I thought I would talk a little bit about the scale of the moon and the size of features that you're seeing when you're looking at the moon. So the smallest thing that you can likely see on the moon is about 1 kilometer. So that's pretty big. That would be you know, a large shopping mall sort of thing size for us here on Earth. So there's no hope at all of seeing, you know, the artifacts from the Apollo missions or anything like that from Earth. Even with Hubble, even the Hubble Space Telescope doesn't have the resolution to see things that are that small. But from lunar orbit, then that you can. So we've certainly received photographs of the tracks of the rovers and the descent modules and things like that from lunar orbit.
Just in case you're looking for something on the moon as a reference point, the moon's about 3,475 kilometers across. So 1 kilometer is actually, like, I would say, pretty decent to be able to see on the moon from Earth.
Yeah. Well, what I was going to say is that in terms of the sizes of different things, let me just bring up my favorites menu here. And I think I've got, here we go. So I've identified a few of the craters on here just to relate back to their dimensions so you can get a sense of it. So this big dark Mare Imbrium area is about 1,150 kilometers in diameter. So 1,150 kilometers in diameter. Sinus Iridum, this is this little bay on the edge of it, which is certainly visible with your unaided eyes on a clear night. That's about 260 kilometers across. Ptolemaeus is this crater kind of near this, just below the center of the Earth-facing side of the moon. So that ring of Ptolemaeus is about 150 kilometers across. Plato, which is the dark lava-filled crater near the north pole of the moon, that's about 100. And actually Tycho is close to that. So Tycho is a little less, we'll come back to Tycho in a bit, but Tycho is around 85 to 100, depending on how you measure it. So that gives you a sense of what you're seeing when you look at the moon. Triesnecker, here's Triesnecker. So Triesnecker is certainly easily visible in a backyard telescope. So there's this crossing point is the middle of the moon, as far as, you know, this is the point that that on average points towards Earth. So Triesnecker is just a little bit northeast of that point. It's 25 kilometers across, to give you a sense of the scale. So that's kind of gives you an idea. So when you're looking at something, you can compare it to some of those well-known features and get a sense of that. All right. So, and also I have I don't know if you put it in the chat, but there's a list of the craters ranked with their sizes and so on from the Fermilab website.
It is indeed in the chat.
The Wikipedia list of craters is not as convenient to work with because it doesn't list them with facts and figures. It just shows thumbnails of where they are. So you have to click on each one to get the information. But the Fermilab one gives you the lunar coordinates and the dimensions in kilometers. All right, so let's talk a little bit about crater types. And then we're going to go into the kind of geological age regions of the moon, the different sort of evolutionary phases. So craters come in different sizes, and depending on their size, they've got different characteristics. So the smallest craters are called simple bowl craters, and they're around, say, under about 10 or 15 kilometers. I'll just bring up that hyperlink with the picture here, so we can show you this picture. So this is what I'm gonna be talking about. So there's a graph of the diameter of the crater versus how many of them there are. And you can see that the smaller craters tend to be these simple ones, and then they get more complicated as you get bigger in diameter, because you've got the impactor that created them had more, delivered more kinetic energy, and so more happened when they occurred. So a simple bowl crater, an example of that would be one called Lalande. So I've got Lalande marked here on this picture. So you can see Lalande is kind of as a simple sharp rim. And let's see if I can have let's try this one. You've got to get a sense that it's got kind of a simple bowl shape. It tends to have a smooth rim under about 20 kilometers, about 1 to 5 diameter to depth ratio. The diameter of the crater ends up being about 10 times as the size of the impactor that came in. So most of the time, these simple craters can have very simple bowl shapes, or they can also have flat bottoms because of material that's slumped in and collected at the bottom. And what you can do is while the moon is waxing or waning in phase and the terminator passes some of these craters, you can look at the shadow cast by the rim inside the crater. And if the shadow that you're seeing is curved, kind of like this one here, then you know it's a simple bowl. But if the shadow has a curved side but a flat bottom to it, then you know that the crater itself has a flat bottom to it as well. So that's one way that scientists can view from Earth and identify the characteristics of the crater without going there. The flat bottom craters tend to be a little bit bigger in size. So they're around 16 kilometers in diameter. The crater Burt is an example of that. So here's Burt. I want to see Burt. Let's see if it's got a flattish shadow. You can see the shadow has a little bit of a flat zone to it. So that's giving you that flat floored crater. So that's something to check out when you're looking at craters to see what kind they are. All right. Then we have craters that are a little bit bigger, and they tend to be also simple, but almost like a pie pan. So a little bit broader, but shallow. An example of that is the crater Sigenes. Let's see if I've got that one labeled on here. I don't seem to have that one on here, but essentially it's like a pie plate. And that would be around 5 to 35 kilometers in diameter, but averaging about 30 kilometers in diameter. And then above that, the craters start becoming more complex. You start getting the central peaks, the more complicated rims, and things like that. So one of the good examples of a small complex crater is Triesnecker. So Triesnecker, you can see that we've got a little bit of action going on here. Let's see if I can get a better view. No, that's not a good one. Let's go back to the default. Here we go. This is sort of seeing it at full moon, where you can see this bright rim around it. That's Triesnecker. So these complex craters can be up to about 50 kilometers in diameter. Their depth to width ratios vary a lot. They can be anywhere from a factor of 10 to a factor of 40. You can get sort of straight segments on the rim. They're not necessarily all nice smooth curves. You can get these concentric slumping or terraces around the edge as well. And we'll come to a better example of that here in a second. And so there are about 80 of these known on the moon, or mapped on the moon right now. But the next size up from this is the large complex craters, and the classic example of that is Tycho. So there's your Tycho. So what happens here is when the impactor comes in, it parts all this energy into the moon's crust. It potentially liquefies or melts the moon's crust in that area. And so it the shock wave tends to move out radially into the moon and radially away from the crater. And then you get rebound. So the moon kind of relaxes after that. And as the material flows back into the middle, it actually pushes the peak up in the center. So that's why you get the central peaks on these. So Copernicus is another example of this type of crater. There are about 45 of these on the near side of the moon that we can see. And you can sometimes, if you've got really good optics or you look for the high res lunar imagery, is you can see that there are terraced walls, and then those terrace walls actually slope backwards away from the center of the crater and have little flat pools where melted lunar crust has actually solidified almost in a very flat surface in between the terraces. So that's cool.
Wow.
Now, around most of these craters, especially the younger craters on the moon, you get the ejecta blankets that spread out from beyond the moon. And a lot of us tend to think that that's, white material, for example, in the sense of Tycho, just white material that was excavated by the blast and spread out. But actually, a lot of the rays that you see on the moon, if you look closely at them, they're actually rows of pits of secondary impacts, so chunks of material that have been blasted out and then fallen back onto the moon in a line, producing a ray. So there's a mix of them, and it's worth looking for examples of both. And then you also get, let's go up to Copernicus here and look for different times of the lunar month. You get different appearances of the craters. So Copernicus actually has a kind of you can almost see it here, a blanket. It's called a glacis, or a rubble sheath, around the outside of the rim of the crater. And that's where the majority of the debris fell and then collapsed into a sloping rampart that slopes away from the main crater. So that's called a glacis. All right, so those are some things to kind of keep an eye out for. Generally, the rule of thumb is the smaller the crater, the more simple it is, and the bigger the crater, the more has gone on. The other thing is that the secondary craters, so the material that's been blasted out of a fresh crater and landed beyond, tends to have less energy than something that's come in at high speed. So the secondary craters tend to be the simple ones as well.
I have two questions. One
Sure.
is for the audience and one is for you, Chris. For the audience, which you're welcome to message or to throw this in the chat or either in Zoom or on YouTube. If you could go and visit any of those types of craters, which one would you go for? And I will reveal what I would do after, so as not to influence
anybody that knows Jenna can guess.
Yeah, it's true. That's very true. And then it definitely doesn't have anything to do with why I'm asking. The other question is from Michelle, which is, have any new craters been identified within the last 50 years or so? And I think the answer is yes. Yeah.
Yes.
Small ones.
So yeah, every now and again we do see something new form. I don't off the top of my head know them, and I don't know that they're big enough to have been labeled on a moon map like Stellarium or Sky Safari, which tends to stick with the larger major features. But yeah, it's over time, this less and less happens. And in fact, that's one way that we use to determine the history of the moon is by the fact that new craters superimpose and partially obliterate older craters. So we can actually judge, how fresh an area of the moon is by how many craters that it exhibits. Mm-hmm. So the dark Mare regions tend to be hardly have any craters at all, and then the high Lantari area tend to be all craters, just one after the other overlapping. I think we'll skip it for today, but in a future session we can talk about the formation theories for the moon and how some of that comes into play in that. I want to talk about, go ahead.
I was also going to mention that actually in a former lunar eclipse, I think it was the one in 2019 maybe, there was an impact on the moon during the eclipse, which was caught by some cameras. There was like a little light flash. So there are new craters forming. It's just that we don't always see them in the process. There's one more question. Do you have time for one more question?
Yeah, sure.
Can we tell the angle of the impactor from the crater?
I'm so glad you asked. We will come back to that. Yes.
Okay.
Yeah.
Okay.
So put a pin in that, and I will definitely come back to that.
And then follow up. We have answers from people who would go to various different places. I think I'm with Dave and Lisa on this one, which is Clavius. I think is really cool because you could climb like several mountains within the crater. So like you could climb the little mountains with the craters in the middle, and then you could go and climb the bigger outside crater walls of Clavius.
Yeah, I might have said that before, but after my research for today, I think I have another idea. Isn't Clavius where the monolith was parked in 2001: A Space Odyssey?
Someone commented that a few minutes ago. Yeah, it is. And it's also another comment from Lisa as well. It's also where water was found back in a couple of years ago, whenever that was.
Yes. So I should say it that I don't, as far as I know, Clavius isn't unique in having water molecules in the rock matrix. I think Clavius was the point on the moon they elected to study.
Right. Okay. Fair enough. So
is that clear?
They tried studying, and then they were like, "Ooh, water," but it may be that there's water everywhere. We just haven't looked properly.
Well, I think they were using the Sophia aircraft-based telescope system, infrared system, and I think they probably had to pick a spot to study, and I think that's where I could be wrong. But I don't think they surveyed the entire moon, and Clavius jumped out as having water. I think it's just, this is the area we studied, and this is what we found. Okay. I think so.
There's one last question from Linda about lava tubes on the moon. Do you want to save that for later?
I didn't have lava tubes in the plan to talk about today, but there's so much that's why I say part one, because there's so many other things we can talk about. What's the comment?
They've heard that the moon has volcanoes that are now extinct, though there are pipes, which I think is meant to be lava tubes. Is it true? If so, how do you know if it's impact craters or a volcano? And I believe it's something to do with the shape, right? Like, because lava tubes are not round.
So lava tubes essentially are places where the lava melted its way as it migrated across a section of the moon, and then drained away and left a trough. In some cases, the trough actually has a lid on it, so it's actually an enclosed tunnel. And in other times, those tunnels have been eroded away and revealed. The tops of them have been opened up. So we talk about potentially using that sort of thing as a pre-built underground base. Mars as well has some of these as well. In terms of volcanism versus other things, so there used to be a lot of controversy, a lot of fights over whether the moon's features were volcanoes or not. We've pretty much pinned down the fact that there were volcanoes on the moon, but they weren't the dominant process that created the features we see on the moon today. And I'll actually come back. I don't know if I've got it mentioned. We talked about it in one of our previous sections. There are a couple of places on the moon where you can see dark. Here we go. Just bring this up here. Can you see where I'm circling?
Oh, yeah.
So this is the crater. Oops, that's not the one I wanted. Alphonsus. It's just below the center point of the moon's disk. Those three, that triangle of three dark patches, are thought to be, pyroclastic or dark cinder cone material that's erupted and then been distributed around a vent on the moon in this area. So there are actually a few places on the moon that you can look for that cover those. So there's that one there. There's also one up here. Okay, so you can see here, this crater here has got two of them at least, and those are another two of those. And these are quite easy to see in a backyard telescope anytime. So just kind of aim, you can ballpark your view. Let me just reopen this one up. There we go. So this is a little better. Yeah, you can just ballpark and aim your telescope a little bit below the center and a little bit to the right, to the left, and you'll pick that up no problem in your eyepiece.
Cool.
All right. So what I want to do is talk a little bit about the lunar basins. So the lunar basins are these essentially the big dark areas that were excavated early in the moon's history. So it actually can be considered the next class up from the crater classification system that I went through before. So once you get past the Copernicus and Tycho size craters with the complex central peak and so on, the next size up are the impactors that were so huge that they carved out these giant basins on the moon. So these are anywhere from a few hundred to up to a couple of thousand kilometers in diameter, the basins. There have been many, many over time. Some of them were erased and replaced by more modern ones. The basins themselves, they don't have a central peak the way craters like Tycho or Copernicus would, but they do often have rings, multiple rings that define them. They have radiating structures. They have lots of ejecta that they've distributed far across the lunar surface. And usually the round shape's pretty apparent, pretty obvious, but sometimes the interior structures, some of the things I mentioned, like the concentric rings, have been flooded over by the subsequent lava flows. And so you've kind of lost them. The rings that I talked about may have been made by almost like the ripples in a pond effect. So when something that large slammed into the moon at such a high speed, it eventually melted the moon in that local area and caused the moon's material to act like a liquid and actually flow kind of like a liquid. And so you can get these almost ripples that are frozen in place once the process is done. So I'm going to show you a cool example of that. And the most youngest basin on the moon is not one we can see. And one of the articles I read talked about if this basin had been facing the Earth when Galileo had seen it, he would have understood so much more about how the moon worked. But because it's partially hidden for us, he didn't see it all the way. And that's that Mare Orientale that I mentioned a little while ago. And this is really cool. So it's the youngest Mare. It's about 3.84 billion years old. It's almost pristine, and it just peeks out beyond the western rim of the moon. And it was discovered in 1961 when Bill Hartmann, who's very famous as an artist and also as a lunar cartographer and researcher, his team was working on something called the Rectified Lunar Atlas. And this is before Apollo. And what they were doing was they were taking photographs taken from the Earth of the moon and projecting them on a hemispherical globe, or basically a 4-foot hemisphere of the moon, projecting those pictures, and then stepping to the side and photographing the objects on the edges from above, quote unquote, from above. Let me just show you a picture of what I mean. So here's the Rectified Lunar Atlas. I'm not sure if I haven't got one picture here.
So essentially adjusting for the skew of our perspective. Yeah.
So for example, this is the moon face onto Earth. So that's the middle of the moon. If I click over here near the right, then you can see this curve?
Yeah.
So that's the edge of Mare Orientale. And there's then another ring inside it.
Oh, cool.
Right? And this is from a photograph taken from Earth. So it's all foreshortened. But by projecting that photo on a curved moon and then stepping over to the side and photographing it straight on, you can reproduce the geometry of that. Let me just go back.
Cool. What a cool idea.
Yeah. Let me do Mare Crisium. So Mare Crisium is here. So Mare Crisium, even though we see it a little bit in one shape, if you were actually flying straight over Mare Crisium or orbiting above it, you could see that it has a slightly different shape. So that was amazingly clever idea. This is a great link if you want to go in and of course the features in the center of the Earth, the center of the moon, will hardly change at all, but the poles and the eastern and western limb would be revealed that way. So here's what I'm going to do. I'm going to take this model of the moon and I'm going to roll it. So let me just see if I can do this one. So here's centered moon. Do this one. And I'm going to roll the moon, pretend that we're able to rotate the moon around. And here's Mare Orientale. So if you can see, the ring. And what I'll do is I'm actually going to change it to a different skin. Let me do this. Surface image model, topography, and boom, there it is.
Wow.
Yeah. So what you're looking at is, let's see, we think that it was formed by about a 65-kilometer wide asteroid hitting the moon at about 15 kilometers a second, or about 54,000 kilometers per hour. It actually happened after the epoch where the moon was, the moon basins were being flooded. So there's hardly any lava filled into it. So it's actually remained the sort of bullseye feature that most of the other mare on the moon have been obliterated, but this one is really, really distinctive. And so you can see that kind of like three distinct rings. Okay, so there's a big ring here, and then there's another ring here, and then there's the center as well. Let me just bring that up. Let's see if I can bring up go back to the original. Yeah. So the outer ring here, this has actually been named the Cordilleran Mountains, so Montes Cordillera. It's about 930 kilometers across. And then inside that, you've got a set called the Rook Mountains with an inner Rook and an outer Rook. So you've got the outer Rook is this ring, and then the inner Rook would be the smallest ring inside. And those are about, I think, 620 kilometers and about 480 kilometers in diameter. And then all around that, there's a zone about 500 kilometers broad of the ejecta that was blasted out by the impact. And you can see all of these radiating structures. And if you magnify them, you can see a lot of those are actually chains of craters. You see all these little chains of craters?
Oh.
So these are the material that's blasted out of the basin and then starts falling and pelting the moon, boom, 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 and producing these linear chains of craters. So the purpose of this is to show you what an ideal lunar basin looks like and some of the aspects of it. And then when you're looking at the part of the moon that we can see, can you recognize some of these aspects? The other thing is you can see here, there's some interior features. So in many cases, what happened is that the basin gets excavated at depth. And then over time, the moon rebounded. That's called isostatic equilibrium. The interior of the basin lifts. And as it lifts, it actually compresses the material inside. And so you get wrinkles forming. And I'll show you some wrinkles in some of the mare that we can see with our telescopes. So let's go back to this main one here. I'm just going to show you another view here. Here we go. So that's Mare Orientale. That's around the side. The other main enormous mare basin that we can see is Mare Imbrium in the northern section here. And you can see this circular shape produced by the mountain ranges around it. So we've got the, we've got the Caucasus Mountains. Caucasus Mountains are the ones on the east. We've got the Alpine Mountains in the north. So this row here. And then we've got the Apennine Mountains in the southeast. And those aren't mountains, they're actually the rim of the crater of the giant basin. So the rule of thumb is when you're looking at some of these features, you want to look for the curved mountain ranges that would be the old rims. You want to look for concentric rings or scarps. So let me just see if I can show you some ring features in here. So you can start to get a sense when you see some of the crinkles that notice the direction the crinkles are moving. They're more or less always arcing concentrically around the center of the basin. So you can look for those crinkles produced by the uplift in the middle. You want to look for craters that have been flooded or infilled. And so what happened is that the Mare Imbrium, or the Sinus Iridum here, the little Bay of Rainbows, was a crater that was there before, but it got depressed by the weight of the lava that filled the basin. And so the rim that we normally would have seen just got submerged, not only by the depth of the lava that flooded in, but also because the whole terrain is tilted down. So it sunk, got lowered down. So the crater is no longer a level crater, it's a tilted crater. You can also look for secondary impacts, and you can look for those linear ejecta features around them as well. So I'm going to skip the formation model stuff. How's our time? Let's actually skip. Yeah, I'm going to skip past the moon ages. So we'll come back. We'll talk about that another day. And let's go to some lunar observing basics. So we'll come back here. Yeah, let's go back. Here we go. So when you're looking at the moon from Earth, remember that the lunar coordinate system is based on 0, 0 is where the point on the moon that on average points towards the center of the Earth. And so this is the moon's equator. So that's 0 degrees north or 0 degrees south. And this is the prime meridian longitude. It's actually close to our crater named BIRT, B-I-R-T, if you want to see the kind of the center of the moon from that point of view. So east on the moon is actually the direction that the rising sun comes from. So when the moon is waxing in phase, the sun is rising over the eastern horizon of the moon. So that's the east is on the right-hand side. If you're in the northern hemisphere, it's on the left if you're in the southern hemisphere. But it's the direction that the sun is coming from when it's waxing. Obviously, west is on the other side. And to help you remember that, I always just think when I'm looking at the moon that I'm looking at a map. So when you pick up a map, you put north at the top, west is in the left, east is on the right, you're good to go. The moon's the same. So the north pole of the moon is only on the top when the moon is above the southern horizon. Because when the moon rises in the east, it's tipped over with the north pole of the moon to the upper left. The moon moves upright when it's culminating over the southern horizon, and then it's actually tips the other way when it's setting in the west. So you can't always assume that the top of the moon is the north. Sometimes it's going to be the upper left or the upper right edge of it.
I have a question that nobody asked. Would the north-south axis on the moon essentially line up with any line that you drew from the north-south axis through the moon? Sorry, from north and south on Earth through the moon. So like if you're outside and you're observing and it's a crescent moon, which would be right on the horizon, if you drew a line from south to north, which would go through the moon, would that line up with the north-south axis on the moon?
You mean if you had you could use the horizon of Earth to? Is that what you're saying?
It wouldn't necessarily be the horizon at any point. Like let's say it's up like 45 degrees. Then your line would go from north up through the 45-degree mark and down to south, like the invisible line that you're drawing, which would mean that the moon would be, the north on the moon would be kind of like at an angle like this.
Here's what I would do, as I would say, okay, where's Tycho, where's Plato? And then the north-south line is just to their right.
Yeah, I'd do that.
Yeah. So just find Tycho, find Plato, and just say, okay, they're roughly that axis. And then you're good to go. That's how I would do it. Yeah. Okay, so that's east, west, north, and south of the moon. Let's talk about a little bit about the phases of the moon. So if you're using Stellarium and you're looking at the moon, you're clicking on the moon at a given point in time, it'll report to you how many days old the moon is, for example, or the moon's age. And those expressions refer to the time that's elapsed since the moon was last at new moon. So the first quarter phase, when the terminator is a straight line from north to south, is about 7.4 days after new moon. Now, Jen and I are familiar, and hopefully a lot of you have watched Jenna's moon sessions talking about the Q days. So the Q days are a tool we use to determine are we before first quarter or after first quarter. So Q equals 0, or Q0 is first quarter. And then Q minus numbers mean the terminator hasn't arrived at the first quarter yet, and Q plus numbers are when the terminator's moved past first quarter. So
if anyone wants to try observing the moon, I'm going to just throw the link to that playlist of the Observe the Moon certificate in there that uses Q days. Q days are a bit odd, but they're useful for some people for visualizing how the moon is set up.
well, it's also useful so you're not chasing things that aren't currently visible tonight, right?
Mm-hmm.
Because you can use those if you sort them by from plus to minus, then you can figure out, okay, where the moon is set up right now, I can use all the +3s tonight.
Yeah.
Or and by the way, if the moon, say the moon is at -2, which is somewhere like this, then anything from -7 to -2 is visible.
Mm-hmm. And the stuff that's at -2 is best. But
Yeah,
everything is visible unless you're at Q day -2 on the waning phase.
Yeah.
And then everything from Q day -2 through to +7 is visible, but stuff on -2 is best.
Yeah. So you can use it to pick the best night to look, but you can also use it to say, I may have missed it at its best, but it's still available. Or I got to wait another night or two for it to move further west for me.
Just before we get too far away from Explore the Moon, I want to plug it as a general observing certificate. One of the things that RASC does is these observing certificates where for Explore the Moon, you do have to be a member of the RASC. It is a certificate where if you see a certain number of things on the moon, in this case, you get a little pin in some cases and a certificate, depending on what you saw them with. We also have one Explore the Universe. We have Looking for Messier Objects. We have Double Stars. Chris was talking about that at the beginning. We have lots. Chris actually has a book out with John Reed, another one of our members, on all of the Messier objects, and I will link that in the chat. Okay, that's enough talk about our certificates.
Last thing about tips for observing the moon: prepare to use lots and lots of magnification. Because when you think about it, the moon has got hundreds and hundreds of nice, fascinating little features on it. And they're all compressed into an area of sky that's smaller than most of the Messier objects. So the Andromeda galaxy is 6 times wider than the moon. That one Messier object is covering 6 more times area than the moon itself is. And the moon itself has got all of this fascinating features to look at, but you've got to crank the magnification up to see it. So also the seeing conditions make a big difference to be able to see the moon when it's not swimming too much. So that's something to watch for. All right, so let's finish up by just highlighting 2 spots on the moon that you can look for some additional aspects that maybe you've missed out on before. One of them is, I'll start with Tycho. So Tycho is visible from about Q+2 and beyond. So once the terminator gets past it, then it's visible for the rest of the cycle until the moon starts to get waning again. Sometimes you can see Tycho even before the terminator has gotten there because it's bright enough to see with Earthshine. So that's the reflected light from the Earth back onto the moon. And it's I've seen reports that you can sometimes see Tycho's rays even on the Earthshine moon, especially with binoculars or a telescope. So that's something to look for. Tycho is so prominent because it's very, very fresh and young. It's about 100 million years old. The floor of Tycho, let's zero in here a little bit. So the flat bottom of the pie pan on Tycho is about 85 kilometers in diameter, but the outer top rim altogether is about 100, 102 or so. So it sort of varies in size depending on what you count. The height of the wall, the height of the rim is about almost 5 kilometers from the floor to the peak. And then in the middle, you've got a complex mountain or split mountain peak in the middle of the crater. And that measures about 2.25 kilometers in diameter. So the central peak is not as high as the rim. So if you were standing outside looking across the rim, you wouldn't see the mountain until you climbed up to the rim. So when Jenna does her future Tycho expedition, she can.
I was going to say, actually, you saying all this stuff makes me think I should change my answer from cloud to Tycho.
That's right. You'll notice that Tycho most of its floor is flat, but there are a couple of zones where there are rubble strewn on the floor. Let me just change my surface image model here and go to my Let's see if this one's better. Yeah, you can sort of get a sense that you've got some flat areas, but you've also got some more rubbly areas in sectors of the Tycho floor. You'll notice that you've got concentric rings around the edge where the rock was not sufficiently strong against the moon's gravity, and so it slumped, and it slumped kind of in a ring. The reason that you get these ring systems is because the fracture, the stresses in the rock are kind of radial in a radial direction. So you get rocks that are all the same radius from the center all have experienced roughly the same stress. And so they all sort of have the ability to collapse as a group, as a family. The other thing is that you can look for these kind of talus slopes, so these sort of avalanches that have slumped material down the rim of the crater. At full moon, let me go back to that other picture here. Let's see the default. Let's see if this one. I'll go back to this other one. Alternate. Yeah, it's hard to see it, but at full moon, there is actually a dark ring around. Dark ring around Tycho.
Oh yeah, you can kind of see it.
Yeah, it's sort of a dark ring. And you've got the dark ring and you've got the ray systems. And what's happening is that the deeper material has been excavated up and spread on around the crater. And over time, things on the moon tend to fade. They're like, putting fabric out in the sunshine where over time it fades. So micrometeorite hits and cosmic ray hits tend to darken bright material and to lighten dark material, so it all kind of becomes uniform. But because Tycho is so fresh, it hasn't happened very much. There's been no time for that melting, that fading to happen. The rays themselves, here's what's cool. The rays themselves, they're not symmetrical. So there actually are more rays in the east half than there are in the west half. And that's because we think that the object that created Tycho came in over the western horizon at a shallow angle and smashed into the moon and spread the material predominantly to the east. So that's evidence for the impactor coming in at a shallow angle. Probably an 8 to 10 kilometer wide object slammed into the moon, creating Tycho. So that's where you get that asymmetric ray system. The other classic asymmetric ray system is Proclus. And you can see here that the Proclus rays are about 220 degrees of the circle. So the object came in just buzzing over the horizon, over the surface, and slammed in here and spread the material east from there. So this could be very shallow impact. Yeah, go ahead.
That answers Warren's question, which was, can we tell the angle of the impactor? And I wanted to touch on the fact that, so it's usually the ray system that lets us figure out some of that information. Almost all craters are circular because it's not the impact itself that causes the crater, it's the explosion of the material on impact that causes the crater. So when it explodes, it always explodes in every direction equally, even if the object is like a weird shape or it's coming in from a weird angle.
That's right, yeah. And everything that gets just melted, anything that's molten or semi-liquid is just going to settle into a roundish shape, right? So yeah. Now this one's this is the dual crater Messier in Mare Fecunditatis, and you can see that there are two rays. The reason it's called crater Messier is because this looks like a comet, and this object came in at only a few degrees above the surface, only a few degree angle, and just put rays out to the west. All right, so that's that one. Let's move on, and we'll talk about the Sea of Serenity. So let me just bring up the Sea of Serenity here. So the Sea of Serenity is in the upper eastern, so the northeastern quadrant of the moon, so the upper right quadrant of the moon. And it's a basin as well. And you can see the basin shape easily in the south, quite readily. So it comes up through this, it's about 750 kilometers in diameter. It's got at least 2, maybe 3 rings, but they're not that easy to see. The main ring is the Jemez Mountains. So where we have our Jemez Mountains here. So we have these sort of mountains on the bottom corner. That's one of the defining edges of the ring. Poseidonus and Lemanier and Shakara, some of these other craters, they're thought to be sitting on the eastern rim of the ring, the main ring. You can look for Mons, let's see, Mons Argeus and Promontorium Arterusia. Those are sort of all forming that ring. The western rim, though, is not as nicely defined because it's bumping up against Mare Imbrium. So this Mount Caucasus, this is part of the big Imbrium basin. So it curves the other way. So it's the bigger, the bigger elephant kind of controlled the structure. There's hints of a bigger ring that run through. And again, I can't necessarily show this in the Starry Night, but when you're looking, see if you can see hints of elevation changes and features that run sort of through Manilius, Maclear, where else? Euxodus, yeah, Euxodus is part of it. Romer's part of it. So they think that if you can kind of convince yourself that there's another ring here, you might be able to see that as well. The inner ring is produced by these ripples and things. Let me just get another image model here. Let's see if the reconnaissance orbit. Here we go. So now you can see these ripples, such as Dorsus Smirnov, and these are kind of concentric to the middle. And these are evidence of the uplift and the crinkling that happens during the uplift. There's also a set of them here in the southwestern edge. So there's a very distinct set of ripples there. And there's some up here as well. So you can look around and see those. Another thing that you'll notice is that the color of the mare varies. So the middle section is brighter, and then you've got these darker rims around the edge. And what we think has happened is that the darker lava filled the basin first, and then about 800 million years later, more lava arrived, and it's a lighter color. And so it's sort of filled in the middle. So you got these darker edges around the outside. Take a look at the place where the Caucasus Mountains and the Apennine Mountains have a gap where they come together, and where you can see I'm just going to show you the topographic map here. And you can see that there are actually kind of elevation changes where the lava that was filling up Serenitatis is flowing outwards through the gap towards Imbrium. And you get these sort of step downs as the lava cooled and paused. So those are things to look for. Let's see. Apollo 17 visited this area. So Apollo 17 landed over here. So here's where Apollo 17 landed, in the southeastern corner between these two kind of mountain peaks. This is the crater Littrow, which is quite obvious in a backyard telescope. And they actually were hoping to find volcanoes. They thought maybe these mountains were volcanoes, but instead they discovered that they're breccias. So they're probably just part of the ring of debris that got blasted out during the creation of the basin. Let's see. Okay, a couple other things to look for. I talked about the rills inside that you can look for. The elevation changes. Yeah, so you can look for the craters like Lemanier. It's one of those situations like Sinus Iridum where the whole terrain is tilted inwards. And so the rim of this crater has now been mostly submerged. You can get some hints of it through here. The Poseidonius is a really cool crater. So this one's got a almost but not quite submerged rim. So some of the lava was able to leak through and infill the crater a little bit. So it's got a very shallow floor, artificially shallow floor. You've got actually a second crater came in later and produced a smaller ring inside of it, which again The western side has lost because it's tipped down and been overcome by the lava that flowed in. You can look for, let me just go back to the other view here. Let's go to the default and see if that works. Here we go. You can look for these little structures that are inside the crater. So again, you've got a curved one here. You've got a ridge that runs in here. And again, this is one of those crinkle ridges from the rebound. Then you've also got a little one here. And if you look closely, this pattern, these are all little pits. Crater, 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 all in a row, little pits. Not sure if you're going to be able to pick those up with a small telescope. You might need a really big aperture and high power to see that. And then you can see the nice simple crater in the middle, the nice simple bowl that we talked about at the very beginning. So this subsequent crater that came in. So those are some things to look for. Another one to mention is there aren't that many craters inside this one, but if you look for Bessel, so Bessel's near the kind of the south central area, and it's got a ray, a bright ray streak that goes through it, and that streak may be coming from whatever formed Menelaus here on the south. So look for that one. And this little bright spot, this is the crater Linné, so you can look for that little bright spot as well. So I'll stop there and take questions.
All sorts of exciting stuff. There's one question from, no, I'm going to start with a later question, get back to the earlier question. Would craters make a natural platform to build a telescope? So I know that they were talking about building a radio telescope on the far side of the moon. Would they be able to use a crater for something like that?
Yeah, so Arecibo was built into a natural valley. And in much the same way, you could select a simple bowl-shaped crater and you'd have your underlying foundation for building a radio telescope. But yeah, you'd want to do one on the far side of the moon. Yeah, good point.
That would be a good start, but I think they would have to probably change the shape a little bit because it wouldn't, I mean, it's really unlikely that a crater would be the exact shape you need for a radio telescope, right?
Well, I'm sure if you were paying for it, you'd want to do an exhaustive search to see if you could find one that would suit the bill, wouldn't you?
Fair
I mean, that would be a great idea.
Yeah.
And now that we have digital elevation models of the moon, so it'd be almost a no-brainer to do a computer search to say, find me a profile that's this parabolic shape.
That would be so cool, just to make a natural radio telescope out of a crater. So cool.
I think you should get on that. Somebody get on that.
There was an article, I think recently, NASA did approve the project to put a radio telescope on the moon, which is very cool. Question from Kathleen: is it possible? This is not. I actually have not read The Apollo Murders by Chris Hadfield. Chris, have you read The Apollo Murders yet? No. Okay. So apparently, in that book, hopefully no spoilies here. Is it possible to have radioactive rocks like in that book? I don't know if they were talking about rocks on the moon or rocks in general.
Well, the current theory is that the reason that all of these mare flooded is because there was internal heating by radioactive decay inside the moon, and it produced the heat and the pressure that then impelled the basalt to erupt and come out. By the way, I didn't show everybody my basalt.
Yes. Can you stop sharing your screen so that we can actually properly see it?
We'll do that.
I was about to say, we want to see your rocks.
Let me do my stop share.
Also, Kathleen has clarified that the rocks were indeed on the moon in the Apollo Murders. Yeah.
So yes, there is radioactive. Would be radioactive rocks on the moon, radioactive elements on the moon, but and we'll do this another time, in terms of the moon formation theory, is that the moon was formed primarily from the Earth's crust rather than the Earth's interior. And radioactive minerals tend to be a little heavier and a little bit sink into the middle more. So the amounts of them would be less. So this is a piece of basalt from Earth, from British Columbia. And can you see that it's almost like frozen slush, and there's a lot of little bubbles and voids in it, things like that. And it's dark and it's heavy. And if I ever see you in person, you guys, I can bring it, and you can feel how heavy it is and dark it is. So this would be the kind of rock that would be in the basalt, in the Mare on the Moon. And just for fun, this is pumice. This is volcanic pumice. Again, you can see all of the bubbles and voids. So this would be more of a, so this would be a lava, kind of a magma type rock. And then this would be an explosive volcano type rock. And the Moon has the same rocks we have on Earth. The compositions, have their own characteristics in a different way, but basically it's the same. So even though the Moon the highlands are made of anorthosite is plagioclase feldspar, and we have lots of that on Earth. Lots of people have it on their kitchen counters.
Oh, feldspar. I know feldspar. There's 2 questions from Linda. What's the difference between wrinkles and waves when you were talking about them on the Moon's surface?
So she may be referring to the fact that I said that the basins may have rings produced partly because the liquefied material expanded and then kind of froze in place at some point. We're not really sure, but there's no, as far as I know, there's no feature on the Moon called the wave. There's the wrinkles are an official type of lunar feature.
Okay.
But they're basically just little ridges.
Okay. And then the follow-up question was mentioning lava. When you say lava, are you referring only to molten rock produced on impact? You're referring to the molten lava that's inside of the Moon. Yeah. That was at one point inside of the Moon.
So when the impact happens, if it's a big enough impactor, the energy is high enough for a lot of melting to happen. Rock melt. That's lunar crust rock that melts primarily. So that's the plagioclase feldspar, the bright stuff. But later on, during that later epoch, the Mare, all those basins that were just sitting there, scars on the Moon, like pockmarks on the Moon, later they got filled in as lava welled up from below and flooded them. And that was molten lava from the heat inside the Moon.
Cool.
Yeah. Thank
you. There's one last question, which I have to admit, I am not sure what it means. So, sorry, Chris. In the Mare that you were just working with, there's a line of craters that look like a strewn field from a conventional meteorite. Is that just a coincidence? I don't know what a strewn field from a conventional meteorite is.
Yes. Okay. Well, there's two ways of looking at this. So there's nothing to say that when something hits the Moon, or the Earth for that matter, that it's a single piece and that it isn't a chain of pieces. So we saw the chain of pieces, fragments of comet Shoemaker-Levy hit Jupiter in a chain, produced a chain of scars. So yes, there's nothing saying that you can't have a group of objects hit the Moon, bum, 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 bam, bam, bam. So that crater Messier showed that was 2 craters. It may have been 2 pieces. It may have been something that skipped. We're not quite sure, but you can do that. And then you can also get, when something does hit, blast material out of the crater, the debris can be a series of pieces. The bigger pieces land first, then the next smallest piece, then the next smallest piece, and so on. The pieces that are lighter can travel farther.
Right.
So you get these diminishing size craters in a chain, bump pits in a radial direction. The Mare Orientale example was a great.
Yeah, that was really cool. I haven't seen that before.
Yeah.
Super neat. Thank you.
Hopefully that answers it, I think.
Yeah. What Mare were we looking at before we went to looking at your rocks instead?
Well, I've only been looking at
Serenitatis, right?
Serenitatis. Let's go back and look at it again. So I was showing.
I think he's probably talking about on the left, because I saw this too. There's 4 in a row, and they're in a straight line a little further up. They're quite far apart from each other, so I don't think that it's
like this.
Yeah, they're just so linear.
Yeah. That's a good thing to look into. Let me just give you the name. So there's Linnae. This one is Rima. That's not Compass. Let's see. Linnae. Yeah. So it's possible that these are simple craters that are secondary, that are radiating from and they could be radiating from another basin somewhere.
Yeah.
But yeah,
Oh.
that's certainly possible.
Thank you, Stephen Dow, who has responded with that they are called Linear A, B, H, F, and G north. Sorry, A, B, F, H, G south to north.
Yeah.
Those are the names. So if you want to take a look, you can. Perfect.
And are they a coincidence, or were they all related? We're not sure.
If you find out, please let us know. I'm not sure we'd even be able to know about that.
But it is possible.
Yeah. And that's it for questions. I know we have one of our attendees. Oh, sorry. Ooh, one last question from YouTube, from Orbis11. Are there any tidal effects on the moon, such as cracks or anything like that from, I guess, the pull of the Earth?
There wouldn't be as many now, because the moon no longer needs to continuously flex the way it did when it was rotating. Right. So as the Earth rotates under the moon,
we flex.
We flex, and our water flows to follow the moon. And the moon used to do that too, but Earth's bigger mass basically stole that angular momentum away from the moon and caused it to stop, to become tidally locked.
So it doesn't flex anymore because
there isn't as much of that.
It's always somewhat oblong shaped, pointed towards us.
Yeah, I mean, well, we know that the moon's orbit is elliptical, so it has apogee, perigee, and there are going to be some stresses that vary over time as well. But I'm not sure that it's significant. The one thing that Stephen Dow has added in the chat, thank goodness we have so many people with lots of experience in our chat. The straight wall, is the straight wall one of those tears? Straight wall is a fault, a scarp.
Okay.
Yeah. Where is it here?
And that's from, okay, that might be from something someone else mentioned, which is moonquakes.
Well, not necessarily. I mean, the moon had some tectonic life to it at some time in the past. And so let's see if I can find the straight wall here. Show it. No. Oh, I can do it this way. There we go. I'll do it this way. So there's the straight wall. So I believe this is a vertically offset fault with the eastern side higher elevation than the western side. And so if you extrapolate the direction, you may be able to relate that to some major feature or major event on the moon. I haven't read up on it too much to know, but yeah. So it could have been a weak point that cracked in the past, and there was some flexure that caused that offset.
All right, thank you, Chris. Who knows? There's a lot of stuff that we know and a lot of stuff that we don't always know the answer to yet. That is going to be it for us tonight, because it is 2 minutes to 5 o'clock, at least for us, and the sun has already set here. So we're gonna call it for the evening, and encourage those of you with clear skies to go out and observe the moon. We had one of our attendees from Cape Breton, who apparently has clear skies right now, say that it's looking really lovely out there. And that the Terminator is going right through one of the main craters, and that isn't that nice. So good views, go take a look, enjoy. And as Eric said, they'll never look at the moon the same way again. And I hope that you feel the same way next time that you go out. Think of how much
that's the idea.
That's the idea. Thanks, everyone. We will see you next time. 2 quick things. Next time, we're going to be talking about holiday gift ideas, and the other thing that I wanted to mention is that tonight, in another 2 hours, we have a talk with the James Webb folks. We have Natalie Ouellette, who is the outreach coordinator, the outreach, like the main outreach point of contact in Canada for the James Webb. She's going to be there, as will Jean Dupuis, who is the senior mission scientist. So if you're interested, there is the Zoom link to register for that event. Just threw it in the chat. Again, that's at 7 o'clock tonight. If you're not videoed and sitting in your chair to out, come on over and learn about the James Webb. Chris,
sounds really good.
thank you so much for all of the work that you put in every time to Insider's Guide. It really is, everyone benefits, and everyone, we all really appreciate that you're able to share so much with us. Thank you so much.
Oh, glad to do it. Thank you.
We'll see
You too,
all-
Jana. You work hard. Very good.
We'll see you all in 2 weeks, and have an excellent half a lunar cycle.
Well, clear skies for the Lunar X and clear skies for the Eclipse, and
Fingers crossed.
maybe I'll have my double stars done by.
Yeah, keep us posted, Chris.
Maybe. All right. Keep looking
Talk
up,
to y'all later.
everybody.